Now that we have built the basic elements for the data path, such as the register file, the program counter that we increment, and we understand that there is an arithmetic and logic unit that receives the values of registers and produce a new value, and we have seen the instruction memory, we can start building what we call the single cycle data path. This is called the single cycle data path because in this design there is one cycle for the entire execution of each instruction. Later on we'll see that we'll evolve this design to make it more efficient, but for now, so that we can understand exactly how the processor works internally, we'll focus on the single cycle data path. So what we need to build the data path, we need to go back and think about the format of the instructions. And to walk us through the process step by step, we're going to start with building a processor that only can execute the add instruction. And then the process will be that later will expand this design so that we can also execute memory access instructions such as load and store. And then we're going to expand it again so that we can execute the branches. But starting with a processor to execute the add instruction, this is the format for the add instruction. And remember that I decode the instruction looking at the opcode and looking at the functions. And then I need to take the value of the two source registers that are specified in bits 15 to 19 and 20 to 24. So I need to take the value of those two registers, send it to the arithmetic and logic unit, and take the result computed by the arithmetic and logic unit and store into the destination register that is specified by the bit 7 to 11. So in this example instruction here, I'll take the value from the registers 18 and 19, and I will write the result into the register 9. So how do I do that? Initially there will be the decoding of the instruction that will be based on the opcode. We're not going to focus on that right now. Let's assume that the instruction has been decoded already and I have found out that I need to execute an add instruction. So in that case, what I'll do, I'll take the bits 15 to 19 from the instruction code, and I will send those 5 bits to specify which register I should read in the port 1 of my register file. And doing that will cause the 32 bits of the register specified. In this example, I'm specifying, this is RS1, I am specifying the register 18. And then I'll take the bits 20 to 24 of the instruction code, and I'll use that to specify to the register file which is the value of the second register port. So in this case, I'll take the content from the register 19 and put in the second port. And remember that I already did the decoding of the instructions. I already found that this is an arithmetic and logic instruction and that this is an add. So there will be several bits that will go into the arithmetic and logic unit for the operation, and we will specify what is the operation that this unit should do to execute this instruction. In this case, I will specify that that's an add. The arithmetic and logic unit will then produce a result. I'll take this result and I need to write this result in register 9. Therefore, I need to carry this result back to the write data port of my register file. That will be a 32-bit line. And now I will take the bit 7 to 11 of my instruction, and I will specify that as the register where I have to write. And now I will issue a command to the register file telling the register file that it must write the value that's in this input data port into the register whose number is specified by the lines 7 to 11 that are coming into the right register specification. So this is how I execute an add instruction. And another thing that we need to focus on is that the arithmetic and logic instruction actually has two outputs. One is the 32-bit result of the operation, but the other is a 1-bit zero output. That 1-bit output will be 0 if the result will be 1 if the result of the operation is 0 and 0 otherwise, and that can be used for branches. So if I want to compare two values, I can take that output. Now I need instructions that will access memory. Instructions that will access memory are the load and store instructions, and because now I'm accessing memory, I need an additional memory in my processor. That's my data memory. My data memory has to receive a specification for the address that will be read. That will be a 32-bit line. And when provided with an address and provided with a signal that says that this is a read operation, the memory will retrieve the data from the specified address and will write into the memory data output. I also can receive a write address, and I can receive a write data. As we see, there is only one address bus that goes from the processor to the memory, so the read address and the write address will be the same lines. And the write data will also be 32 bits, and when I need to write into this memory, I'm going to have a memory write signal that will become active to indicate that I need to write. Recall that when I do a load and store instruction, I have to take the immediate field from the binary representation of the instruction and sign extend it to 32-bit and add to the value of the base address that's specified by a register in the processor. So in order to do that, I need a sign extension unit. This is called the immediate generation unit, and the immediate generation unit will take as input all the 32 bits of the instruction code, so the entire binary representation of the instruction, and will produce in the output a 32-bit value that is the value of the immediate sign extended to 32-bit in the case of a load or store. In other instructions, it may zero extend that value. And the reason that you need to take all the 32 bits as input for RISC-V is because RISC-V has different formats for the immediate depending on the instruction, the format of the instruction. Remember that there is that shuffling of bits that happens in RISC-V to make the hardware operation simpler. So the immediate generation unit has a 32-bit instruction as input, and it will select a 12-bit field from for the load or the store or the branch instruction, and will sign extend that into 32 bits. So the very same unit works for all the instructions that have immediate value. And if I want to think what sign extension means that I take the most significant bit of the smaller representation and I simply copy to the higher bits. So copying in this case means simply taking a wire and take additional wires from that line. So now that I have my new components that I have for my design is my data memory that I just described, my immediate generation, and my register file, my arithmetic and logic unit work exactly like it did before. So let's see how I execute a load instruction. Let's recall that for a load instruction is an instruction that brings data from the memory into the processor. And I specify the address in the memory where I fetch that data by specifying a base address. In this case, I specify X9. And the value of this address, the number of this register appears in the bits 15 to 19 of the instruction format. So to execute the instruction, I must get the value that is in that register, and I need to add to it the immediate value. In the case of the load instruction, the immediate value is specified in the 12 most significant bit of the instruction. I need to sign extend that, and then I need to add the value of the register specified in the bits 15 to 19 to the value of the immediate specified in the bit 20 to 31 after sign extension. So in terms of my design, I'll take the bits 15 to 19 of my instruction code and I'll provide as the read register 1 of my register file, which will cause that register, the 32 bits of that register, to come out of the register file and be provided to in this representation here to the top input of my arithmetic and logic unit. And then what I'm going to do, I'll take all the 32 bits of the instruction and I'll send to the immediate generator, and I'll be telling the immediate generator that I have already decoded this instruction by examining the opcode, and I already know that this is a load instruction. So I'll provide that information to the immediate generator, and with that information, the immediate generator will generate the correct immediate value. This will be a 32 bit that's formed by those 12 bits sign extended to 32. So now I need to tell the arithmetic and logic unit that it needs to do an addition so that it can compute the address. And the output of the arithmetic and logic unit now is the address that I need to send to the memory. And because this is a load instruction, I will send that address to the read address of the memory. But as I mentioned before, the read address and the write address actually come from the very same bus. So I send that address and I provide that address both as a read address and as a write address to the memory. And I tell the memory that this is a read operation. So when I tell the memory that this is a read operation, the memory will fetch the data from the address specified, and the memory, the data that comes out of the memory now has to be written into the destination register. The destination register is given by the bit 7 to 11. So what I need to do now is to take the data that the memory produces, bring all the way back to the right data entry of my register file, and specify to the register file that I want to write into the register whose number is given by the bit 7 to 11 of the binary representation of my instruction. And of course, I then need to tell the register file that this is a write operation. So this is how I do a load. I process a load instruction. The processing of a store instruction is similar to the load in the computation of the address. To compute the address for the store, again, I take the bits 15 to 19 of the instruction, and I take all the 32 bits of the instruction I provided to the immediate generator, and I tell the immediate generator that this is a store operation, so that the immediate generator knows to take the bits 0 to 4 from the bits 7 to 11 of the instructions, and the bits 5 to 11 from the bits 21 to 31. So it will go concatenate those bits and then sign extend them to 32 bits to produce the second value that goes into the arithmetic and logic unit. Now I'll tell the arithmetic unit to add those two numbers, and then I'll provide the output of the arithmetic and logic unit to the both read and the write address of the data memory. But now this operation is a store operation. So what I need to do, I need to take the value of the register that is in bits 20 to 24 of the instruction code and send this to the memory, because that will be the data that I'm going to write in the memory. So I specify to the register file that I need the register file to retrieve the value of the register whose number is specified by the bits 20 to 21 of the instruction. And when I take this value, I do not send it to the arithmetic and logic unit. What I need to do is to send it to the memory. So I send it to the memory as the write data, and I tell the memory to write that data into that address, and that's the end of the store instruction. I do not have to write into the register file when I do a store instruction, because the store instruction does not change the value of any registers. So if I now combine my add design with my load and store design, what I have is that I am specifying, so I have the 32-bit immediate value that comes from the load and store instructions, and I have the 32-bit register value that comes from the add instruction. So how do I, if I have the situation where I have those two values that need to go into the second input of the arithmetic and logic unit, how do I decide which one we're going to go through? Well, I use one of those switches that's called a MUX, and I have a control signal for that MUX that says which one is the source for the arithmetic and logic unit. If this control signal is 0, then the value of the register that came from the register file will go to the arithmetic and logic unit. So I'm going to make this control signal equals 0 when I have decoded the instruction and the instruction was an add. And I'll make this equal 1 if I have decoded the instruction was either a store or a load. In that case, I'll send the immediate value into the arithmetic and logic unit. So this is a good moment for us to stop for a second and think about how hardware works. So in the hardware, in the case, for example, of a load instruction, the second value that comes from the register file is not used by anybody because, remember, for the case of the load instruction, I'm going to add the value of the first register to the immediate value, and then I will take the value from the memory and bring back the register file to write into a register. So I never use the second output of the register file when I'm executing a load instruction. However, the hardware will retrieve that value anyway, and that value will come into these lines and will be provided to this input of this MUX and will be provided to this input of the memory. However, it's the control signals that will prevent that value from taking any effect into the state of the program. So the fact that this arithmetic and logic unit source is selecting, in the case of a load instruction, this input makes the value that is in input 0 irrelevant because it cannot go through. The only one that can go through in the case of a load is this value. Same thing here in the memory. The fact that I sent data to the memory, if I do not activate the memory write, which I will not going to do for a load, will make this the data that is in this entry meaningless because it's not going to be used by the memory. So it's just a side note to note how hardware works. Often what would consider work is done by hardware when it's not necessary, so that the design is simpler. So this is how I use this MUX to select the input, the second input to the arithmetic and logic unit. That could be the value that comes from a register or could be the immediate value depending on the opcoding instruction. I do the decoder to make that decision. And then the same thing happens for the value that I'm going to write into the register file. If I'm executing an add instruction, the value to write in the register file has to be the value that comes from the arithmetic and logic unit. If I'm executing a load instruction, the value to write into the register file must be the value that comes from the memory. Therefore, I need another one of those switches here that will decide which one of those two signals we're going to go through to go to the register file. And this switch is called the memory to register switch. So if I say memory to register equal 1, I'm connecting the output from the data memory into the register file. If I say memory to register equals 0, I'm connecting the output of the arithmetic and logic unit to the register file. So this is what we had for the design of the data path for memory access and for adds. I will stop the recording here, and then in the second part of this lecture, we're going to see how we do design for branches.